Before putting circular functions completely off to the side for the rest of the course, I thought it would be good to do an example problem with circular functions, which we're going to do here, and then in the next video, we'll do that same problem with trig functions. I think this will be helpful to further illustrate exactly what the book means when it defines circular functions, as well as this will illustrate how anything that you can do with circular functions, you could do the same thing with regular trig functions. So, okay, what we're going to do is we're going to do a simple model that is tracking the height of someone on a Ferris wheel. Okay, so here's, I think, the most well-known famous Ferris wheel in the world. This is in London. This is the London Eye. It's roughly about 400 feet in diameter. And what we want to do is make a simple model that gives the height of someone on the Ferris wheel above the ground when they're on the roller coaster. So like, you know, this person here, how far are they above the ground? We'll call that H. Okay, and we'll say that this height here is 20 feet. Okay, and so in this video, we're going to do this using circular functions. And so the main idea with circular functions is that you want to really remove yourself from trig functions. We're now going to be working with circular functions. These are functions that are used to model something dealing with a circle. It's all about circles. We don't care about angles or triangles. It's not that you can't use angles or triangles if you want with circular functions, but in general, you don't have to. Circular functions, by definition, have no association with an angle or a triangle. And in the previous video, I went into detail about why that is precisely the case. Okay, so here are the circular functions. You know, you see sine, cosine, secant. Well, no, these are associated with the trig functions. Technically, no, not at all. We could put completely different names here, and based on the definition of circular functions, you know, I could put 3 random letters here, and based on the definition of circular functions, this would work fine. So again, in theory, you can use these functions to model anything that's dealing with a circle. Or, I mean, you could expand out from outside of a circle, you know, if you can just add more algebra and whatnot. But in general, these help you model anything that's either dealing with a circle or, you know, it's associated with a circle. Okay, now these are defined based on a unit circle. You need a unit circle to define these. Okay, the input into these circular functions, the input is an arc length on the unit circle measured from where you assume the 0 position. So this is x, y. This is a unit circle. You assume the 0 position is where the circle crosses the positive x-axis, and then you're measuring the arc length counterclockwise from there. So the input is an arc length on the unit circle. Okay, so again, the input here, this is s. S can be from 0 to the full arc length of a unit circle, which would be 2 pi or more than that, or you could put a negative input, whatever. So you input this arc length, and then the output is, so this is the x coordinate of that point on the circle, the y coordinate of that point on the circle, and here's the y coordinate divided by the x coordinate, and then these are reciprocals. Okay. So there's the London Eye diameter. Let's say here's the ground. Now, with the circular functions, we need an xy coordinate system. And obviously, what we want to do is let's put that xy coordinate system at the center of the Ferris wheel circle. Okay, the diameter is 400 feet. We'll just put the radius. And then this distance here is 20 feet. Okay, and the goal is to use the circular functions to get h. Okay, but h is a function of what? A function of time? Well, okay, no, the way we're going to look at this is, let's imagine that every bucket has some kind of transducer on it, and the signal that it communicates to the operator at the boarding point, the passenger boarding point, it communicates a number between 0 and 100. That number represents a percent, and it's the percent that that bucket is around the circle, with the 0 position being here. So the number at this point on the operator would be seeing on the computer screen would be like 19%. Then up here would be getting close to 50%, then 75%, and then once it got back to like 100%, it would go back to 0. You can think about, okay? And we'll call this number P. You know, if the bucket is sitting still, then the P on the computer screen is just a steady number. If the Ferris wheel is moving, then it's like a live updating number. Okay, so H is a function of this P here. And what we want to do is we want to imagine that we're going to write some code into the software to where corresponding to the P value for the bucket, we take that P value and we put it into a formula, and associated with every P value is a corresponding height. It gives you the height of the bucket. And we're going to do that using circular functions. So how can we do this? Well, okay, let's think about, so we'll put the circular function coordinates in standard position. So S is equal to 0 here at the positive x-axis, and you go counterclockwise from there. And so associated with the bucket at each moment in time is a corresponding arc length value around the circle, a corresponding S value, right? At this moment in time, the bucket has a S value associated with it. So this arc length here is associated with this bucket. And well, actually, we're going to call that S prime. And why? Because it's not the same. The S here, these S's that you input into the circular functions, those are corresponding to the unit circle. And in fact, so are these X and Y coordinates. So what I'll do is, let me update this. We'll call this X prime and Y prime. And then you got S prime. Okay, and so at any moment in time, the bucket also has coordinates. So, you know, this is X prime, this is Y prime. And then I'm not going to draw S prime, but just imagine S prime is there. This arc length, that it's not including, this is not included. But the entire rest of the arc length of this circle is the S prime of the bucket here. Okay, but the only data we have is the size of the circle and the P number. That's the only information we have, and we're going to use the circular functions to put it through like a formula and get an H value out. How can we do that? Well, okay, when working with the circular functions, there's kind of two approaches you can use. You can input into the circular functions an arc length value and get out coordinates, X and Y coordinates, or you can you have X and Y coordinates and you input those in and use like inverse circular functions to get out an arc length. We're going to be inputting in an arc length for this problem. Okay, but we can't input S prime. Well, first of all, we need to figure out how to determine S prime. We don't even have S prime yet. But once we have S prime, we can't just input that into the circular functions because this S is associated with a unit circle. And these coordinates are the coordinates of a point on the unit circle. Okay, but first, before we can even think about this, we need to determine S prime given a P value. How do we do that? Well, okay, let's think about what if the loading position were at the positive x-axis point, hypothetically. So the 0 positions of S prime and the loading point, or in the P variable, the 0 positions were at the same spot here. For that scenario, what would S prime be? Well, that's easy because what you do is what's the full circumference of this circle? It's 2 pi r, so 2 pi times 200 that's 400 pi. Okay, and so all you would do is just take the full circumference and multiply it by p. Right? Because, okay, if p is 0.25, then what should s prime be? Well, if p is 0.25, then you would be here. That means that s prime should be 1/4 of the full rotation, and there you go. 0.25 times 400 pi. P is 0, s prime is 0. If p is 1/2, that means s prime should be 1/2 of the full rotation, and that's exactly what you would get. Okay, but in actuality, the p value start point is offset from the s prime start point by a 1/4 of a rotation. And so what we need to do is we need to adjust p here, like shift p. Okay, and we can think about how to do this in the sense that, so when s prime is 0, what should p be? P should be 0.25, right? If s prime is 0, that means the bucket is here. That means p would be 0.25. So, okay, 400 pi, we want to shift p, is equal to 0. What do we need to do with p? Well, we just need to do this. There you go. P is 0.25. This equals 0. So we're going to say that s prime is 400 pi times p minus 0.25. And there you go. We can check this. So let's see. When p is equal to 0, what do you get? It's minus 1/4 of the full circumference. And that's what if this is 0, you go minus 1/4. You're at p is equal to 0. What about when p is equal to 0.75? That means that the bucket is here. That should be half of a full rotation. 0.75 minus 0.25 is 0.5, and there you go. Okay, so now we can input p and get s prime. That's the arc length position of the bucket with this as the 0 point. So from s prime, how do we get s? S being what we're going to input into whatever circular functions we end up using. Well, okay, so s, again, it corresponds to an arc length on a unit circle. Has to be a unit circle. So if you think about it, this s prime here is per 200 feet of radius. If we take s prime and divide it by 200, what you get is something that's per 1 foot of radius. It's that arc length on a circle per 1 foot of radius. So we've effectively converted that arc length into an arc length that corresponds to the arc length on a unit circle, which is what we need. So S is going to be S prime divided by 200. Okay, so now we start with P and we can get all the way to S. So now with S, we can use the circular functions. Okay, so now when we input S, what we're going to get out are either an x coordinate, a y coordinate, a ratio of x and y coordinates, or a reciprocal of the x and y coordinates. But remember, these x and y coordinates correspond to a unit circle. It's a position on a unit circle. Okay, now for this problem, all we actually need is a y coordinate. So we're going to use, all we need to use is sine of S, and we're going to get y. Then we need to convert y to y prime, right? Once we have y, we need to get y prime. Okay, so we're going to do, from here, we're going to do sine of S is equal to y. But now how do we get from this, how do we get y prime? Well, there's two ways of looking at this. One way is you can think about y is So if that's a unit circle, that's not drawn to scale, obviously. Okay, then the y coordinate, not y prime, just the y coordinate, is this. This is the y coordinate, right? This is x. This is x. This is y. And then this has a radius. The hypotenuse here is 1. You can see that you have two similar triangles here. So we could take, with similar triangles, the ratios of the sides of the triangles are the same. So you could take the radius of the hypotenuse of the larger triangle, so that's 200, divide that by the hypotenuse of the smaller, and that's equal to the side length of the larger triangle divided by the side length of the smaller. And so you get y prime is equal to 200y. So there you go. Now we've converted from y to y prime. Or if you don't want to use triangles, you can think about it. So if you wanted to scale up a unit circle to any size, you would multiply each of the x and y coordinates by the amount you want to scale it up. Okay, so if you have, so r is equal to x squared plus y squared, the square root of that. If you want to scale up the radius by 2, then multiply each of the coordinates by 2. There you go. You've multiplied the square root of x squared plus y squared by 2. And so knowing that, what you can think about is you could approach it to that any time, you know, for this problem, we're only using this one y coordinate. We would multiply it by 200. But if we were using, you know, multiple circular functions, then any time you ever got an x or y or both or whatever, you'd multiply that coordinate by 200. So you'd have 1 over 200x. Here would just be 200x. Here, it's a ratio, so it doesn't matter, right? 200y divided by 200x is just y divided by x anyway. And so again, so since we're only using sine of s is equal to y, we would just know that to convert from y to y prime, we just multiply that y coordinate by 200. Okay, so we convert from y to y prime by just multiplying y by 200. Okay, so now let me erase this. If you go through all of these formulas, we start with p, and from there we can get all the way to y prime. So once we have y prime, how can we calculate h? Well, okay, if we look at this particular position here, what you can see is that what we need to do is we need to take 200 plus 20, that's this full distance, and subtract this value from it, or this, at least the magnitude of this value, and we'll get h. But we need to do this correctly because in actuality, y prime here is a negative value. But just thinking about this as a magnitude for the moment, the idea is we want to add up 200 plus 20, this whole length, and then subtract from that as a magnitude, take out this amount. And then we've got h. Now, thinking about it from like a point over here, here's y prime. You know, that's y prime. What we want to do is we want to take 200 plus 20 and add this value to that. Okay, so what we need to do is, the formula is going to be that 200 plus 20 is 220. And if we add y prime to that, that's going to give us h. And I'm saying add because here y prime would be negative, so we would get 200 plus 20, and then this would end up being minus. But if y prime was up here, you would take 220 and then add the y prime to it. Okay, so let's bring that over here. H is equal to 220 plus y prime. Okay, there we go. So let's bring all this together. Y prime is 200y. So, okay. H is 220 plus 200y. Okay, but y is sine of s. So 200 sine of s plus 220. Okay, but s is s prime over 200. Okay, so h is 200 sine of s prime over 200 plus 220. Okay, but s prime is this here. So h is 200 sine of okay, we can simplify this. So h is equal to 200 sine of 2 pi plus, and there you go. There's h as a function of this input data point p determined using a circular function. Okay, so now the whole point of this was to help you understand what's meant by a circular function, the meaning of a circular function. But as I've mentioned, we're going to put this circular function idea off to the side going forward. And so with that, what I want to do in the next video is we're going to solve this problem again using the trigonometric functions, which is the same thing, but we're going to kind of allow ourselves to think in terms of radians and angles. Okay, see you in the next video.